Okay. So let's take a look at today. Are we excited? Are you guys excited? You're all excited, right? You're happy to be here. Oh yeah. Yeah, just full of joy. Full of joy. You know how much time I had to prepare this lesson? What noise scared you? There was a noise? What noise? Does it give you a noise when I hit record? Was it just me? Does the noise of my voice scare you? Oh, there is a noise for that. The one that says the screen is being recorded? That's funky. Huh. I have no idea. I don't know what that sounds like. It doesn't show me. I'm gonna go into the settings and find it at some point and be like, oh my God, does this scare me? Am I going to put it outside during Halloween? I don't know. Anyway, you want to see how much time I had to write this class yesterday? That's how long. Look at that. That's so sad. That's so sad. That's so sad. But it's all going to be functions and fractional exponents. Having this little slide is a stayover from when I used to put every single little header on every concept that I would put on there. I don't think that's too helpful. I don't think that was coming in handy, and I think it was just in the way. So I'll probably just skip that at some point. But I'm really anal about these things. So next time I teach this class, that slide's going bye-bye. Okay. What happens when I ramble? I need water. Not regular water because that doesn't have enough of a flavor. I put strawberry lemonade next to this guy. Okay, cool. That makes me happy. All right. Let's do this. So we're reviewing probability. So probability wasn't bad, right? It's how likely an event is to happen. So as it says, when you flip a coin, you have a half of a chance it'll land on heads. So the probability is 1 out of 2 or 50%, or the decimal 0.50. Most of the time you're probably going to deal with the fractions or the decimals, not as much the percentage. It comes in handy and it helps to know how to shift that over into a percentage. But really, when you say the probability is like 0 point something, that's more than acceptable. So we got a bunch of the stuff, bit of a rehash from the last time, but we're going back to Mr. Bag of Marbles. We had 5 yellow, 5 blue, 8 green, and 7 red. So the probability of grabbing one at random and it's being yellow would be saying, okay, I got 5 yellow. I added all those up. There are 25 marbles. So guess what the probability is? 5 out of 25. It's literally just your chances, right? And you can reduce that. You can always reduce probabilities, despite what some instructors have said, and I will fight them to the death on that. You can reduce them, deal with it. And if you add the probabilities of all possibilities together, you always get something that reduces down to 1, which is 100%. So if the probability that an event happen, here's a separate thing. If the probability that an event will happen is something, I put X, but whatever. Probability of event is something, and all the probabilities have to add to 1. Then you could say that the probability that that thing will not happen is 1 minus the thing, 1 minus X. So that's the complement. If this thing happening is X, then everything else is 1 minus X. Because it's 100% minus whatever the heck that was. Not too bad. That comes in really handy in situations where you have a bunch of probabilities being options that you can add together. And then it's a lot easier to find the complement of something that's not going to happen than it is to add up all of the possibilities of each little thing happening. So if you just have to rule out one thing, that's your best bet. So like it says, the probability of grabbing a yellow marble, I almost said yarble. The probability of grabbing a yellow marble is 1/5. So the probability that you won't grab one is the rest of it. That's 1/5, and then the rest of it is 4/5, right? So you do 1 minus that 1/5, you get 4/5. Boom, that's its complement. We're happy, right? So similar to when we did independent and dependent variables, there's independent and dependent events with probability. Those are just classifications. It's a little easier to understand them than it is to play around with the variable ones, because the concepts are the same, but with probability, you're usually dealing with real life concepts rather than random algebraic structures. So it's a little bit easier to see. So in some cases, the first event happening impacts the probability of the second event. So I walk over to the light switch, I hit a button, the button switches off the light. That influenced that. So that means that the act of me pressing the light switch was independent. Nothing made me do that. No thing according to chance just shifted me to hit the light switch. But the dependent event from hitting that light switch is the light turning on or off, right? So it's entirely dependent on that. I can't go and psychically turn on a light and have it flip the switch across the room. That would go the other direction. So you can't depend on that happening the other way. So like it says down there at the bottom, flipping a coin multiple times, that's a bunch of independent events in a row. You like if I flip a coin and I get a heads, if I flip a coin again, I can't say because I got heads, I'm going to get. Doesn't influence that at all. You're just flipping a coin. So those are all independent events. So here we have the rules on adding and multiplying probabilities. So same marble stuff, but if you had to have the probability of something being either one option or another option, well, you would just add those options together, right? If there are 8 green and 7 red, and you're seeing what the options are for what the probability is for getting either a green or a red, well, there's 8 green, there's 7 red, so to satisfy that, there are now 15 possibilities rather than just one or the other, right? So that's when you add the probabilities together. When you have, usually the word or is a big indicator, but generally the concept is when you are having to kind of put together a couple of options. Now the big one with the bold word I got there, and the big one with that is that we end up multiplying, because in probabilities like that, it involves one event happening and another event happening. So essentially, you're not looking for, oh yeah, the first event happened and maybe the second event happening. No, you're looking for only the spot where both of them happen. So in that case, you end up multiplying the probabilities together because you have more possibilities happening that way. Like when we build a tree diagram, those branches are getting out of hand at that point. There is no way you could convince me to make a tree diagram with the yellow, blue, green, and red right there. And just imagine that you have probabilities outside of 1 digit. It'd be horrifying. I don't want to see that. I don't want to look at it. I don't want to think about it. These are things that are better done on paper. So that's very useful with independent events, because independent events, cool. What's if I flip a coin? I got one out of 2 chances it's going to hit heads. Okay, if I flip the same coin or flip a different coin, I don't care. You got the same chances. So the chances that you'll get heads both times is 1/2 times 1/2. So you get 1/4. Okay, but if it's dependent events, those tend to get trickier. And you see that I have an example on drawing cards. Usually when you look up a lot of problems for probability, you'll most see like marbles, flipping coins, card decks, because card decks are kind of universal. You get the general idea of them. You know, half of the cards are black, half the cards are red. You have 4 suits. You got Jack, King, Queen, Ace, and then 2 through 10, through 9. They're 10. I don't care. I don't care enough. Yeah, so it's a pretty standard setup. So you'll see that happen a lot. So if you're drawing cards out of a deck and you're being asked, hey, what are the chances that both cards are going to be black, right? Well, you pull one card out and say that one's black. Well, that's 26 out of 52 possibilities right there, right? So there's 20, because half the deck is 26. You pull one out, cool. We've gotten one of those 26 out of those 52. But the next one, the next time you pull a card out, did you take that card and put it back? No, we're trying to pull out 2 cards. So the next time you pull one out, well, how many black cards are there? 25 now. How many total cards are there? 51 now. So it goes down. You have less possibilities, which means that was dependent on the previous one. So that's usually where the dependent and independent ideas come into play. You're not going to, if you have to do probability stuff, if somebody doesn't ask you specifically which one's dependent, which one's independent, it's not really going to matter. You have to just be able to judge, hey, is this going to change with the next one? That's really what's going to come in handy when you're doing these types of problems, is this going to change based on the previous event? And if it does, cool. Change what your next one is. If it doesn't, cool. Probably do the same thing. I don't know. All right. Hey, look, tree diagrams. We love tree diagrams. I refuse to do tree diagrams with more than 3 options because it gets horrifying. I've had to do tree diagrams with 4 options and it just branches out like, oh my God. Like every time I do it, I don't make the first couple wide enough. And if you don't make the first couple wide enough, you end up scrunching at the end. It's awkward. It's horrible. So of course, the probability tree diagram just gives you a visual representations of all your probabilities. So you never start at heads or tails in this instance, but you always kind of start from like one point and you branch out into the possibilities of what you're doing right now. So if I was rolling a die from that one spot there on the left, it would branch out 6 times to 1 through 6, right? And then the next time you roll the die, from each of those 1 through 6s, it would branch out again to 1 through 6, over and over and over again for however many times you do that. And you can imagine that gets very, very, very big, very quick. And that's just with things with small options. So tree diagrams, they're awesome for understanding this stuff. you're probably not going to make anything bigger than what you see on that screen there. If you have to do a tree diagram, they're probably not going to hate you that much to do that. So you always have it branching out to the options. The branches coming off of those options always add up to 1 because, hey, after if I'm doing something, there's 100% chance that something's happening, right? So if I flip a coin, okay, there's the awkward, infinitesimally small possibility it could land on the edge. But we're just going to say it's not, right? It's going to land on heads or tails. So you have 2 options, heads or tails. Probability of each is half of your options. So on each of those branches, you get 0.5. Now, what is the probability of getting tails on the first flip and heads on the second flip? Well, if I was to check that out from the very beginning, I would say, okay, I'm going to go down the branch on tails. So we have a 0.5 there. And then we're saying we get a heads on the second one, we're going to go up the branch on head, right? So we have a 0.5 and then a 0.5. So the options of that happening are when you multiply those 2 probabilities together. Same as with the word and on the previous slide. This is just a visual representation of that happening. So if you understand the previous slide, you're probably not going to need to make a tree diagram. But they sure as heck help if you're confused. So you'd multiply those together, half of a half is a fourth, boom, you get a fourth of an option. And you can tell that because if you look at that blue area on the right, it lists all of your options. How many are there? 4. What are the chances we're going to have that happen? 1 of them out of the 4 of them, period, right? If I said, just looking at those outcomes, if I flipped a coin twice, what are the chances that I'm not going to hit the same side? Well, that would count heads and tails or tails and heads, right? That's 2 out of 4 possibilities. Cool, breaks down to a half. So there's a 50% chance that you're going to end up with either the same side or 2 different sides when you flip 2 coins. I feel like I've talked too much about that. Let's look at problems. I only did a couple of problems because I feel like the explanation part is really the most useful. And honestly, we did a lot of examples last time. I think we were feeling pretty good on probability. So this guy says, given a standard die, determine the probability for the following events when rolling the die twice. I'm just writing die twice in my notes, and if anybody looks at this out of context, I hope they're like freaked out a little bit. I'm not gonna lie. So let me just make some notes of the questions here. Sheet papers where? Go. Over to notes. Die twice. Drama. Okay. So we're looking for the probabilities of rolling a die twice. And then that first, that we get an even number, then we get an odd number, right? Okay, well, you have the numbers 1 through 6, right? I'm going to write them out because they might come in handy. Not necessarily on this one, but you know, that's one possibility. So you have 1 through 6 as possibilities, right? So if I said, okay, what's the probability I get an even number? 2, 4, 6, there's 3. What a surprise. So 3 out of 6. Okay, odd numbers, 1, 3, 5, cool. That's another 3 out of 6. Since we're looking for the probabilities of both events happening, we are going to multiply these two probabilities together. Now, before I do that, I'm going to reduce them because that's going to give me less of a headache. You can absolutely reduce early if you can. I like doing it. You like doing it. Makes our lives easier because I would much rather do 1 times 1 and 2 times 2 than 3 times 3 and 6 times 6. It's not that either one is particularly hard. It's just that I don't want to reduce that thing. I don't have to reduce this if I've already reduced. Multiply through, you get a 1/4, and we are happy. We are happy, right? Okay. So what about the probability that we get a 4 and then a number less than 4? Okay. Okay. Now that could be fun. That could be fun, right? Now, yeah, it could be interesting, right? Okay. So if we roll a 4, how many times what's my chances of rolling a 4, right? Once. Yeah, there's only 1 4 out of the 6 options, right? Then it says rolling a number less than 4. Okay. Well, how many numbers are less than 4? 1, 2, 3 of them, right? Okay, 3 out of 6. Well, I'm going to reduce that. So we have 1/6 times 1/2 now, which gives us a 12th. You have a 1 out of 12 probability there. God, we're just one step away from doing expected value, and it's not on the high set, it's not on the GED, and I really want to explain it because it's kind of useful. Kind of useful. I'm gonna give you guys a rough, useless lesson at this point. Just for funsies, funsies. There is a concept in probability called expected value. And essentially what that means is, think about it as betting. Let's say that I hit a 6, I get $100. And if I get If I get 3 through 5, I get $5. If I get 1 or 2, I get $1. So essentially what expected value is it's calculating the probability, like the eventual average value of doing something. So if I did this 100 times, what's the value? Well, the probability of getting a 6 is 1/6 times its value. And then you would add, 3 through 5, that's 3 options. So 3 out of 6, 1/2, you get $5. And then 1 and 2, that's 2 options out of 6. That's a third of an option, and you get $1. And you'd be able to multiply this out and add them up and say, okay, that's the expected value of doing it over and over and over again. Why am I telling you this right now? I don't know. We live in Nevada. It's a gambling state. And I guarantee you, if you sat there and did the math on any single thing in the state of Nevada, that has you put money into it, if you calculated that out, every single freaking one of them would have a negative number at the end. Every time. Because eventually, they want you to spend money, not give it to you. Something like this, yeah, it gives us money. But what if it suddenly costs $10 to play? Well, that would go down by 10, that would go down by 10, and that would go down by 10. Suddenly, these are negative numbers. And these probabilities are a lot higher than that one. You do the math enough, and as long as these guys are negative and they outweigh the positive, you're making money. Isn't that fun? Isn't that fun? No, you don't need to know this, but it's kind of nice to know it right now for living in Nevada. Cool. Nice sideline thing, right? I really just wanted to go over that. I haven't done that in like 3 years. I just kind of felt like it. You ever have somebody who's like, I just kind of feel like showing you this thing with math.
The 1/2 on I get on the 3 and 5, but the 1 and 2, you got a 1/3.
It's because this would have started as 3/6, and this would have started as 2/6.
Yep. Okay.
Yeah.
It's
It's cool. It's cool. When I was writing that out, I'm like, I feel like I should probably not reduce these because I'm gonna throw people off. I'm like, yeah, let's take that chance. No, I threw you off. It happens. All right. Well, getting away from Mr. Random freaking thing that you don't need to know. What about rolling a 1 twice? What are the shots of that? That sounds a lot easier than that, right? If I roll a 1, what are my chances? I got 1 option, right? If I roll another 1, what are my options? Another 1. Okay, 1 times 1, 1. 6 times 6, 36. 1 out of 36. That is the lowest probability that you can get if you're rolling a die twice. You can't magically make something worse happen, right? So Snake Eye is kind of nice. You roll doubles, you should feel decent about it. There wasn't much of a chance of that. It's like a 3% shot. It's good stuff. That's good stuff. So does anyone have questions on probability before I teach you new stuff? Random questions are cool. Doesn't have to relate to this. You can easily stump me. I don't know a whole lot about probability. I'm not going to lie. I never took statistics. You know, it's really surprising that you can get, I have associates in math. Didn't need to take statistics. I figured that out really quick when I was working at what was the tutoring center. And anytime somebody came in with statistics homework, nobody could help them because everybody was in engineering stuff and none of them had to take statistics. Not a single freaking one of them took statistics. It was bad. Luckily, we actually had the statistic teacher on staff, so that was great. That was her only saving grace. Like, no, you need to come back when Jim's here. Wait for Jim. He'll fix you. Okay. Hey, look, we got new stuff. I love new stuff. And so you know, it's going to be a little bit till we get some actual examples. So the next several slides are conceptual, and they're good to get down. And it's not hard. It's kind of weird looking. It usually confuses the heck out of people, but it's not bad. It is legitimately not bad. So functions are kind of special equations. We're used to equations, right? Like y equals 2x plus 1. Cool, that's a line. We're happy about that. But for it to be a function, it has to relate an input to a single output. It only has one output. So if I, like 2x plus 1 would work, because if I threw something at x, I would get a y, right? And you might look at this and be like, how often am I going to plug something in and get two things? Well, when you get to higher level functions, you get to higher level equations, it happens all the time. Sometimes you'll, like, just imagine a circle. Think of x as your inputs, think of y as your outputs. If I had a circle, every single freaking input would have two outputs, right? Because it would cross, it would have two values for that x. So anything that's kind of circular is a function. I like that I didn't even read over this slide before I started talking, and I had a circle on the freaking slide. I like it. You can see that that's the obvious option. I mean, I'm not gonna tell you guys a freaking hyperbola. You don't know what that is. We're not gonna play with conic sections. Oh man, those were fun. Both college algebra and calculus 2 very frequently would go over conic sections at the same time. There's literally a chapter in the middle of the calculus book that's basically a review, and the assumption is that everybody forgot it, and it's true, they did. They all forgot it. I could teach people in calc and college algebra at the same time. Loved it. Very convenient. So, useful things on this slide. The idea of functions relating one input to one output, and what they're called. So you can see that inputs are usually the x's, outputs are usually the y's. That can change based on, honestly, just which examples which variables you're using. But it's almost always the inputs are the horizontal axis, and the outputs are almost always the vertical axis. So as long as you get that idea, that's great. And also what the inputs and the outputs can be called. They're called the domain and the range. And even though one of them is called range, they're literally both just ranges of values, right? So if I had a line segment, not a line, but a line segment that started at one point and it ended at one point, the x values from here to here would be the domain, and the y values from as low as this goes to as high as that goes, that would be the range. There is a slide that talks about that and gives that explanation a little later, so you can always pull that off of. Honestly, you could Google domain range and find a billion things explaining it and a billion charts, but this is already in the Google Drive. You can just take a look at this slideshow if need be. So, naming functions. This is where I usually lose people. This is what usually confuses people. It's not too bad. Just think of it right away as that f of x thing on the left. So f parentheses x, that's one thing. That's not two variables. That is a thing. That is the name of a function, and then in parentheses, it is which variable you're using. So in this case, it does say, hey, that's the input, right? So it's saying this is a function, we're calling it f. Why do we call it f? Usually you end up with f of x. Why? This function starts with f, so it seems like a good one to go with. That's literally f of y. So you'll see f of x the most. You'll see g of x second at most, and then h of x, literally because those letters come after f. Mathematicians have no imagination at all. None at all. Myself included, I have none. So just think of that f of x equals being essentially y equals. Just in this case, instead of y equals, we have, hey, this thing's named this, and this is going to be its variable. Okay? So as I have here, there's no significance to y and a y equals. So we actually give it a specific name by putting a letter and then putting the variable in those parentheses. So that way, if I have multiple functions I'm dealing with, and usually a good example of that would be sometimes you're doing a word problem or you're working stuff out and you'll have a formula for the cost of something, the revenue of something, and the profit of something. So you'll have different functions and you'll say, okay, well, they're all dealing with dollar amounts. Dollar amounts are X's across the board. Am I going to call them all Y equals? No, that's going to get really confusing really fast, right? I'm going to say the cost is C of X. The revenue is R of X. The profit is P of X. Boom, we're good. We gave them names. We can differentiate between them. And we can look at that and say, cool, they all have the same variable. We're happy. We get the idea. That's pretty much why you have this happen, right? So you always have just whatever your function name is, a letter of whatever's going on in parentheses, that's your variable, equals whatever the heck is happening here. So it says here what to output. That's probably a better formal way of looking at it. But it's just whatever the heck's going to spit out. You put in something in for that variable on the right, it's going to give you what spits out from that. Okay. So just because some problems don't have a function name and they'll have y equals, they could still be functions. If you have something that would work out as a function, it's still a function. It doesn't have to be specifically named something of X. It doesn't have to. So like this says here, y equals X squared. Cool. Well, you still have an input. There's still a relationship from the input to the output, and you have an output, right? It's going to spit out to Y. Okay, that's still a function. That's fine. So it says here there are two special rules. It has to work for every possible input value. So, I mean, if I'm just doing some obscure mathematical thing, I can plug in -5 billion and it'll work. But if I'm dealing with dollar amounts, and we're not talking about my bank account, you're probably going to avoid negatives. So yeah, those are the possible input values. It doesn't mean it has to work for every value, but in the context of what you're doing, it has to work for all the values that matter. And it only has one relationship for each input value. That's basically saying, hey, if I plug one thing in here, it's going to spit out one thing. It's not going to spit out two. It's not going to give me, well, it might come out to be this. No, it's always going to spit out a thing. You put in one value, you get one value as an output. So you can kind of see what's happening with the input output thing. One thing in the input has to have one thing in the output, right? So it says here, one to many is not allowed, but many to one is allowed. So what that's telling you is that outputs, you can have the same output more than once. That's okay. If, you know, you're measuring, I don't know, say you're measuring borrowing $5 off of a friend or something, or borrowing money off of a friend, and this one gives you $5, this one gives you $20, this one gives you $5. Cool, that doesn't make it break by both of them giving you the same amount. But as long as you're not trying to hit up the same one twice, that's the idea there. So Yeah, I like that. I would keep writing a circle to get an example. One to many is not allowed because that again is one input getting two outputs. Many to one is allowed because those are completely separate inputs. They might hit the same output, that's okay. A good example of that, my go-to example of it is a sine wave, and if you don't know what that looks like, I'm literally gonna just jump to the notes because I assume that my hand gestures won't be seen by all in the camera. But a sine wave is a function and it looks like that. You've probably seen stuff like that. Okay, without that weird edge happening there, that was my bad. But yeah, no, it goes on forever, just having a wave, right? So if I was looking at like this spot right here and I said, hey, that's its Y value, that's the output. Well, that same output happens here, 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 here. That's fine because each one of these, as it moves along, different input, different input, different input, different input, different input, all the way across. So it is a function. And graphing wise, there's a very, very easy way of keeping that in mind. Based on how I'm talking about this, I'm gonna go to this slide first. Okay, yeah, I don't think this breaks anything. I want this slide first. So if you think about a graph, it can't pass through one input more than once. So the vertical line test is a really easy way of just, honestly, I've always just kind of used my pen and scanned across an example. And if it crosses that line more than once, it can't be a function, right? Because if you look at that right one, where it says not a function, the funky looking one that looks like an S, where it has that line, there are three values. That's three outputs from one input. So that one can't work. But the one on the left is a function because every single possible vertical line only crosses through that graph once. Just once. That means it all has one output for each of those, so you're peachy. So a nice thing to be able to do is say, honestly, when I was getting asked basic questions on this stuff after I bought expensive fancy calculator, I literally just threw them at the graph part of my calculator, and I was like, yeah, it's not a function. Because you could just eyeball them at that point, right? Really easy to deal with. Now, one thing I have on here that's important to note is that thing on the right, what we're learning right now doesn't mean that can't happen. It just means it's not a function. So it's still an equation, it's still a curve, it's still a line, whatever. If it crosses more than once, all that's telling us is that it's not specifically a function. It still exists. It's just not hitting our criteria right now, right? So you'll often see evaluate this function. And I'm suddenly disappointed in myself for not having a good example on this page. That would have been a good idea. So evaluating a function just means work it out at this point. Because usually you'll be given some function, f of x is equal to x squared plus 2x plus 5 or some funky thing. And it'll say, hey, evaluate f of 3, for instance, f of 3. Well, if normally we have f of x and suddenly we have f of 3, well, that tells me that my x's are turning into 3s. So you would take that 3 and just throw it at your equation for every x. So it's just like plugging a value in. It's just easier to tell you, hey, f of 3, instead of, excuse me, could you go to that specific example and plug in this number? It actually works out a little quicker to be able to find those values, to be able to, particularly if I'm working with like a table of values, if I'm finding a bunch of things, it's more convenient to have function notation. So here's what I was talking about when I said that I would have a visual representation of domain and range. So I like how this graph sets it up, because I usually have students get really kind of confused over doing domain and range. Sometimes I'll see people say that the range is going from like the top part to where it kind of like curves around right there under the 2. I'll see people do that, but it really is literally just domain is all of the x values it covers, and range is all the y values it covers. So it's literally, when I ask somebody to tell me what their domain and range is, and they're stumped a little bit, I say, okay, domain. How far left and how far right does it go? Because that's literally the answer. As far left as we go to as far right as we go. What about range? How far down does it go to how far up does it go? That's it. If you think about it that way, you are peachy. That is it. We don't care that it squiggles like crazy in the middle. I don't care at all. All I care about is how high it goes and how low it goes. That's it. Which is which, domain and range. So if you look at the domain line there, which axis is that kind of running across? Horizontal, right? So that is actually going to be your x values. Domain is on your x values. Range, that's going height-wise, right? It's going up, it's going down. That's your y values. Now, again, you might not have an x, you might not have a y, you might have c of x, the cost function that we mentioned before. And then you wouldn't have a y-axis, you would have a c axis. But it's the same thing, right? Just different names for the same stuff. It always works out to be basically the y values are your range, the x values are your domain, or whatever happens to be standing in for those variables for that point. Hey, look, we got a bunch. We got a bunch. Now, this looks hard, but they're not. Actually, everybody, give me a minute, because I'm going to make this at least a little bit harder. Uh-oh. 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 Did I accidentally hit F11? Oh, God. Oh, God, get away. All right. I don't care about your HTMLs right now. Let's see. Let's say that we had a function f of x is equal to, I don't even care. Let's say 3x squared plus 1/2 x minus 1. I don't know. There's a minus 1. Why not? Let's say that we needed f of 3. We needed f of 0. And we needed Nope, nope. Let's make it a little easier on you guys. There we go. There's a reason for that, and the reason is what I was about to do is going to make literally no sense and be impossible for us tonight until I cover the next lesson. So we're not gonna do that. We can't do that yet. That literally, we're gonna break stuff if we try to do that. I don't know. There we go. Let's do two of these. Let's do, I don't know. 31. 31's a nice number. What the hell happened here? Why are you over there? There we go. I feel better. Okay. Why are you over there? Get over there. There we go. Okay. This is literally how I set up my homework. It's kind of depressing, isn't it? All right. So kind of a throw together problem, obviously, just threw it together. You don't necessarily need to put the parentheses when you write it down for the 1/2. I just do that to show that that's fraction on my page without writing it, without getting a symbol for fractions. You're wondering why I got quiet. I'm writing them down. I don't know why I didn't have any examples like this. What the hell's my problem? This is like half of it. This is what you're gonna do with this stuff. You're gonna have something that says f of x equals stuff. And we're gonna use stuff to figure out some values, right? Cool. Well, f of 3. This stuff right here, I am tutoring somebody on the side who is in Math 126, which is pre-calculus, and they are confused as hell by this concept. Most people are. When you first do this stuff, it throws you off, right? So always kind of look at this and say, okay, well, f of 3, it's asking for f of 3. Well, what's f of whatever? This is basically our y, right? So this is saying, hey, our variable x is 3. What's y? We can use y for now. It's good to understand it. We understand what y is, right? This is basically y equals. Okay, so what that's telling me is that, all right, this is my x. I'm going to plug it in, right? Oh, I hate myself for using a 3. Whatever, I don't care. They should have been even numbers. Whatever. All right, so f of 3 is 1/2 of 3 minus 1. And for the sake of being lazy, because let's face it, I am, half of 3 is 1.5. That's right, I'm jumping to decimals because it's a lot easier to not have to show you guys breaking down these guys with fractions right now. That's not the lesson. The lesson is understanding the f of stuff. I don't actually care if you understand what the answer to this problem is. I care that you understand getting it. That is all that matters right now. The 0.5 here that we're getting, that doesn't matter. I don't care about that. What matters is the journey, man. It's the journey, man. my really bad Tommy Chong. Right? Cheech Chong? Anybody online? Nobody? You gotta respect them. Stoner comedy still is comedy. I might not be a stoner, but I don't care. All right, so we got f of 0. That's the next one. This is again telling me x is 0. I have no idea on why. Right? Okay. So f of 0 is plugging in a 0. 1/2 of 0 minus 1. Okay, what's half of nothing? Nothing. If I have nothing, and you take $1 away from me, now I have debt. -1. Hey, that symbol right there is it's kind of looking like what my bank account's gonna look like tomorrow when I go pick up pre-orders at GameStop. I want my Bayonetta 3, all right? Coming out tomorrow. I have the expensive one on order and I just have $5 on it. That's my own damn fault. All right. Okay, so f of whatever, pretty basic, right? Not bad. And until you understand it, if you are working these on your own, you go onto essentialed.com, you start working out some of those problems that it gives you, write this next to it, at least until you understand fully what it is you're doing. Because that is the biggest mistake I see with anybody doing these types of problems. The absolute biggest mistake I see is people looking at this and thinking that's the y value and then solving it for the x. Happens constantly.
That's what I thought at first, but
Oh yeah, 100%.
until you did, that was like perfect.
So that's why I like to explain it this way, because a lot of teachers will just be like, oh, this, therefore this. No, don't do that. People's brains gooey right now. You teach them new things, their brains go, right? Like, how often you been in a math class? It's been too hard for you and you forget how to add 2 and 2. It happens. I tutored once for 6 hours straight and it was all really tough stuff. And then near the end, somebody asked me a question. I start working it out and they're like, wait, how did you do that? And I'm like, I just factor out a 7 from a 10. 7 doesn't evenly go into 10. I did that. When you're learning new stuff, your brain is mush. And when you do too much math, your brain stays mush, right? Okay, so f of x is 7. Well, what is f of x? Well, remember, that was basically what we were saying is similar to y equals, right? This is telling us that y is 7, and we want to know what x is, right? So what that's telling me is that this thing over here is a 7. So we have to solve for the x. Which, of course, we can add the 1 over. I have 8 is 1/2 x. I multiply the 2 over. Run out of space. I get x is 16. And there we go. We got a number. Again, I don't care what that number is. I care that you understand this. Man, if I assigned homework, I would be the king of partial credit, right? But also, I have assigned homework before. You know why you guys don't get homework? Because I have a day job. I have a full-time job. I assigned homework for one class. There were like 5 students total. at the beginning. It took me forever to grade everybody's homework. Teachers got it bad. This is why everything's online now. That's easy. You just plug it in once and everybody just hits it. Spits out a grade. We're happy. Something go wrong? Cool, email me. Easy, love it. Okay, what about f of x is 31? That's telling me, again, y is 31. So what is our x? Okay. So again, we're going to set the equation equal to that 31. And we're going to solve for it. Add the 1 over, we get 32 is equal to 1/2 x, multiply 2 on both sides, and we get 64. Right? 64. So again, f of something means, hey, your variable is that something. Plug it in and figure it out. So you could see that, hey, whatever this thing ends up being, whatever these are the outputs, right? F of x equals 31. That means some variable plugged in for that x gave us a 31 as an output. Now, the whole stressing input and output thing, it comes in handy to understand this stuff, but you might be asked, hey, how often am I going to need to truly understand what an input and an output are? Not too horribly often. Not too horribly often. It's a conceptual thing. It helps you understand functions. It helps you understand what they are, but things you got to get down. Domain, range, the function notation that we got, and understanding what that vertical line test was showing you. It is showing you that, hey, every input only gets one output. You get that idea down, cool, you got functions. Happy with functions. Functions aren't too bad. They are equations, just with a little bit more strict specifications, right? And that's pretty much it, right? So there we are for the analytical stuff, which isn't bad, right? Let's jump over here. We have more examples. Now these examples are easy because, and every time I go over them, I keep thinking next time I do this, I'm going to draw out these graphs in advance so I can just show you guys right away. I'm never going to remember that. That is not going to happen. So what I'm going to do, I'm going to draw the graphs of these guys really quick. And we are going to look at them and decide whether or not they are functions. It's going to be the first time you see the pergolas. And are you ever going to see one again? I don't know. You ever going to go higher in math? Because if you do, yes. If you don't, no. In case you're wondering how I can make rough graphs of these very quickly, it's because once you learn them, they are all quite simple concepts. Now, could I have gone online and found some better graphs that would make a little bit more sense at this level? Yes. But it seemed more fun to give it like kind of a preview to some of the uglier stuff that pops up later. Because the cubic functions definitely pop up. The conic sections, so like parabolas and hyperbolas, those pop up a lot, particularly hyperbolas. Parabolas, not much. Or other way around, hyperbolas not so much. Parabolas all the time, all the freaking time. So all we're going to do is determine whether or not these are functions. Number one, we got a circle. Is a circle a function? It is not a function. Not. Think of the vertical line test. Vertical line test. Pass a vertical line through this guy. If it hits more than once anywhere, it is not a function. Okay, what about number two? We got a straight line. Look at that straight line. That is the straightest of straight lines ever. It's beautiful. It's beautiful. Is that a function? Pausing for dramatic effect. Making people think for half a second. It is. It is a function.
I was hitting one.
Yep, vertical line test. Does it have, there's two ways to look at this. Vertical line test. Yeah, it only passes through once, but I have a 2x minus 1. Is there any x value I can plug that in right there that's going to spit out more than one thing? Nah, right? Whatever I plug in, it's just going to be 2 times that and then subtracted 1, right? Doesn't matter what, it's never going to spit out 2 things. So it's a function. Y equals x squared, number 3. We have that sort of thing. It's like a U that goes up forever in both directions. There's a parabola. So something like that. Is that a function? Yeah, right? Because vertical line test, it only passes through that curve once, right? At any vertical line. Just putting FNC for function because honestly, I'm just lazy and I don't want to write out function. But yeah, again, if you looked at it analytically, x squared, is there any number where if I multiplied it by itself, I would get 2 numbers? No. So that one has to be a function. Now, this one's a little trickier, number 4. This one's a little trickier to conceptualize. X equals y squared. So y is the output, right? X is the input. Well, it might be useful to understand it right now, might not, I don't know. But I did say at one point when we were going over square roots, I said, hey, if let's put this in the margin over here. if I was to square root both sides. Now, at the time, we were only looking at the positive numbers, but technically, if I square root a number and x is a number, we don't know what the number is. Depends on where you are, right? But x is a number. And if I square root that number, what do I get? Well, it could go two ways, because if I had the negative of it, it would square to the positive. And if I had the positive of it, it obviously squares to the positive. So we get a plus or minus. Now suddenly, is there anything I can plug in for x that gives me more than one y? Well, we have a plus or a minus. That gives me both a positive and a negative answer. So in fact, other than plugging in a 0 right there, every single thing along this curve is going to spit out two outputs, right? Every single thing like completely horribly fails that vertical line test. And that is why it's that plus or minus thing right there. If I square root both sides, technically you get a plus or minus. Very useful to know when you get this stuff. Bless you.
Okay.
So that is why this one is not a function. Bless you again. Okay. Probably starting to get the idea pretty good now. Let's look at number 5 here. Number 5, we have y equals x cubed. These x cubes usually intimidate the hell out of everybody, but what I usually tell students is, hey, it's kind of like a parabola, but if I took that left hand side of it and I just flipped it downwards. That's pretty much what's happening with these guys, okay? Now, same idea. Is there anything I can plug in for that x that would spit me out more than one y? No. If I multiply something by itself 3 times, it's going to do exactly what multiplying by itself 2 times does. It's going to give me a freaking number, right? Okay. And again, it passes our vertical line test. So it is a function. Now, 6 and 7 are weird looking, right? And you might look at this and be like, what the hell? What the hell is happening? Would you believe the formula for these are basically like an ellipse, but inverted? It's kind of funky. It's literally just one sign difference. So conceptual wise, these hit when you hit something called conic sections. And if you don't care about anything you don't need to know right now, this is where you can turn off your brain for a minute. Because basically, conic sections are exactly what it sounds like. They're sections of a cone, a couple of cones in this case. And if I decided to take like a sheet and I cut straight in right here, you could you would have like a weird little hoop happening right here and a weird little hoop happening right here. This is that hoop. So that's basically what these are from. So if you're curious at all, you can hit the Google, look at them. You are literally almost, if you're keeping up with me so far, you're almost to the skill level of just working these guys out. Like after the next couple of sections, you're probably like right there. Then they're not bad. Okay, the formulas for them look horrifying at first, but working them out, it's okay. Literally, algebra from here on out just means the problems are getting bigger. The rules are still the same. but the problems get bigger. So this is when the problems get bigger. So horizontal hyperbola, number 6, is that a function? Oh, hell no, right? Because again, it's kind of like having the y squared on this last one. Kind of like that, happening almost twice, right? What about the vertical hyperbola? Is that a function? That might be confusing to conceptualize, but you have to think of this as being one graph. Even though there are two curves happening, it is one graph. And since this is one graph, again, it will not pass the vertical line test. Because even though they're two distinct pieces, this guy and this guy, they're from the same equation. When you hit these hyperbola things, that isn't two separate equations, that is one equation. It's kind of funky how you graph them too. Because you end up taking stuff from the equation, making a little box, drawing diagonals through the box, and saying, cool, through those diagonals, you'd actually have something like this. Pretend I didn't just cut through that. But you would have something kind of like that. You end up drawing this box, you end up drawing diagonals through the box, pretend those lines went through the diagonals, because God, I'm awful with this. And then you would be like, cool, I'm going to draw a curve that way, and I'm going to draw a curve that way across my diagonals, and we're going to call it PT. So yes, you do end up graphing these. And no, it's not a nightmare, but it's really freaking weird at first. And the funny thing is, the same values, if I flipped that thing, I would end up having an ellipse in that little box. They're like inverses of ellipse. I don't understand the relationship there. I'm not even gonna pretend like I do, but that's kind of what happens.
So what's the equation of that hyperbola,
All right,
please?
let's see if I can find my usual go-to. I already found my go-to. I would, when people were in this section, I would print off this sheet and I would say, cool, this is the entire chapter that they would go over, right? Isn't this horrifying looking? I love it. Yeah, so look at the equation of an ellipse and look at the equation of a hyperbola. They're so freaking close to each other, right? One has a plus and one has a minus. Yeah, it's kind of horrifying looking. But weirdly enough, when you get to this point, they're honestly not that bad. They are going to scare the hell out of you, but they're not that bad. But yeah, I literally, every time I have to pull this up, like, God, someday I'm gonna search it and it's not gonna be there and I'm gonna be at a loss for words and just confused as hell because I have used this sheet over and over for like 15 freaking years. Not even joking. What is that? Why does that one have better colors? Where did it go?
Oh.
What is that? What is happening? Oh, you're oh, you jerks.
You gotta sign me.
I hate that. That's bull. That is bull. I want to see it with the cool pictures on the side. Ah, dicks. I mean, that's kind of what's happening. Yeah. Cool. You don't need to know any of that. These are nicer. These I'm not going to write down. These are easy. Do the following tables represent functions y or y not? So let's just look at number 1. Kind of visualize it. You got x values, you got y values. Okay, so what do we know about functions? For every one input, there can only be one output. And our inputs are X, right? So we do have a couple of repeats on that X, right? We have the 0.25 and we have the 0.26. Well, 2.5 and 2.6, those would be right above each other, right? Well, since I have one input that's giving me two separate outputs, that one on the left, not a function, can't work, cannot work. Just because you have,
2 2.
yeah, we have two inputs, we have two twos that go to different outputs. If I had 2.5 and 2.5, I might look at this and be like, why the hell is this written twice? But it would work because then it wouldn't be a separate point. Now, number two, we have a bunch of numbers ranging from 1 to 6. And if we look at the y's, we do have a 5 twice. Is that okay? Is that okay? It is okay. Because those are separate inputs. All of those inputs are different. Each one has an output, just one output. If I had a comma on one of those y's and had another value, thing would break, right? Because I'd have more than one point there. That'd basically be what's happening on number one. But for number two, even if you hit that same y value, it's kind of like that sine wave I showed you. It can hit that same y value over and over and over again. We don't care about that as long as the input has one output. Again, I'm gonna scroll up. 1 to many is not allowed, but many to 1 is allowed. So that, think of that as X to Y is as the relationship, many to 1, many X's to 1 Y. Yeah, that's allowed, we could do that. But 1X to many Y's, that is not allowed, that breaks. Imagine domain is on the left, range is on the right. Okay. Pretty decent, right? Now this one's fun. Why did I make this difficult looking? Why did I do that? Why did I do that? So this one is another one that we are going to just follow along with Ben's graphs. But we're actually going to have answers for them. So again, give me a moment to draw them. Oh, yep, got a nice blue streak on the side of my hand. Love being a lefty. If you know someone who is left-handed who has to write things a lot, and you need a good Christmas gift idea, Google quickest drying ink for pens. Just get a quick drying ink pen. It is life-changing. I am so tired. When I would do this stuff in pencil, the entire side of my hand was silver.
This, I used to do this backwards because it's hit me all the time.
Yeah, yeah. Oh yeah, 100%. Being a lefty kind of sucks. But yeah, quick drying ink. Oh, awesome. Okay, so where? Yes, that one would be down here. Negative, no, okay. Now, for these answers, I would want these guys to be given in interval notation. Now, if you haven't learned interval notation yet, you're about to get a crash course. I did go over it in my previous class. I like to cover it, even though it may or may not be in the HSE or GED, because you will, if you're doing this type of math, It's like the gold standard for how you're writing things down. Now, what the hell is that answer? What did I do with that? Okay. So despite the laziness involved, these graphs are accurate. Now, number one is kind of cheap because I didn't draw any points on it. But the values we need, we can eyeball no problem, okay? So for number one, we are again looking for domain and range. So the way I usually do it is I'll put a D and an R and I'll say, okay, these are going to be my answers. So again, domain is all of the inputs. It is all of the X values. So as I like to say, domain would be left to right. Whereas range, that's your outputs, that's your Y values. So these ones you go down to up. Now that's a weird phrase, but it makes sense with what the way we're using it. Okay. So for domain, well, this guy's going up like this, right? And that little arrow there, that means it's going on forever. Okay. So the question is, domain-wise, left to right-wise, does this ever stop going to the left? Does it ever stop going to the left? If I had y equals x squared, could I plug in -5 billion? Yeah, I could square that. I don't want to, but I could. Could I put in -5 billion to the 100th power? Yeah, you could. I kind of don't mind squaring that one because I would change that 1 to a 2, but that's, that's pretty much it. So this guy actually, it doesn't end up going, stopping to the left. They also don't stop going to the right. Now, granted, the way it's kind of exponentially jumping up here, you're going to get some big freaking values the further you go, right? That's why usually when you graph these, you graph them really close to the middle here. But it doesn't stop going left and it doesn't stop going right. So there's a couple of ways of writing the domain. The way I prefer, the way that is kind of universally accepted, is called interval notation. Now, if you're not familiar with that, because I know a lot of you haven't been in my class before, you gotta write it down. And I highly recommend looking up maybe a 5-minute video on YouTube or something. There's probably a Khan Academy video that's 2 minutes long that would be oh, like everything else that freaking guy does. Love him, hate him, because he's so much better than I will ever be. But whatever. It's called interval notation because you're literally writing it out as intervals. Okay, so you kind of think about it on almost like being on a number line. So you'd say, okay, how far left is this going? Well, it doesn't stop, right? It goes to infinity. Now, if it goes to the infinity to the left, you end up saying, okay, negative infinity and positive infinity are different directions. So you say it goes to negative infinity on the left, and you can't include the last number in negative infinity, so you use a parentheses. With interval notation, anything you can't include uses a parentheses. Anything you can include uses a bracket. So they're kind of set up like points that you put on a graph. You would put a comma right here and say, okay, well, how far right does it go? It doesn't stop, right? It keeps going, same as the left. I could plug in a quadrillion. I don't even know what number that is, but it sounds fancy. I could plug that in there and it would spit out a number. So it goes on forever to the right. So we would have negative infinity to positive infinity. Now that's all well and good. Man, I'm just now realizing that every single one of these problems is gonna have the same domain. Man. I have another random example down here, and it's gonna be stupid and pretty basic. It's gonna be a line segment. Okay, I have a random example down there. Don't worry about it yet. All right. So range-wise, range is the y values, right? Range is how low it goes to how high it goes. Okay, so how low does this thing go? Well, it stops right here, right? It stops and turns around. So the lowest value here would be 0. So I always start from the lowest to the highest value. And does it include that 0? Does it stop at that 0? It crosses that 0, right? So we would include that. We put a bracket there. That shows that we're including that value. Now, does it ever stop going up? That's a lot easier to understand than the left and right one, right? Clearly, it never stops going up, right? So that one does go to infinity right here. Okay, not too bad, right? Kind of weird, kind of funky, but it's doable. Okay. All right. Same shape, different spot. Same shape, different spot, right? Why is this the same shape? Well, if this is an x squared, things you're not going to know for a while. This is an x squared being moved to the right 2 times and down 4 times. Again, if you're curious about these are called transformations. And again, this is something you would cover, say, college algebra or pre-calculus, whichever one. Honestly, they're the same damn class. I don't know why there's 2 different ones. You take a pre-calc class, there's a 50-50 shot at having a book that says college algebra or pre-calculus. It's kind of funny. So this is a transformation of this. That's basically meaning that, hey, this is also in the shape of an x squared, but funkier, right? Same with this guy actually down here. Now, all we're worried about, because right now we don't care if it moved left, right. It could be flipped upside down. It could be under the table. I don't care where it is. All I care about is how far left and right it goes and how far down and up it goes, right? So domain, well, it's the same shape. And the same shape in a different spot. There's nothing I can plug in here that's going to break this equation, right? Like even if I plugged in a 2 and I would get 0 squared, okay, that's 0 minus 4. All right, cool. That's actually this point right here, which is called the vertex. So there's nothing I can plug into this thing to break it. Again, it's the same shape. So we're going to have the exact same domain. It never stops going to the left. It never stops going to the right. So it's a negative infinity going to a positive infinity. And the range, well, the range, just like the other one, it stops, right? So how far down does it go? 1, 2, 3, 4. Okay, all right, well, it seems to stop at -4. Okay, so that means this thing's range starts at a -4 and then goes up forever. So we have -4 to infinity. Do I have any questions so far? I love questions. If you have questions, I want them. Throw them at me. Go out of your way to make something stupid up. I don't care. I'd like some questions. What does this have to do with peanut butter and jelly? Nothing. Anything, nothing? Okay, cool. All right. So for number 3, we have an x cubed. Now, don't stress the shape. Stress what we need. We need to be able to identify the domain and the range. That's what we care about. How far left does this go? Well, keeps going down, right? But does it keep going to the left? Does it curve around? What happens below this part of the graph? Well, it follows whatever I would plug into x cubed. So is there anything I plug into an x cubed? Is there anything multiplied by itself 3 times that wouldn't exist? No, because numbers keep going, right? I could plug in negative whatever, I could plug in positive whatever. Goes left forever, goes right forever. So the domain on this guy, annoyingly enough, on all 4 of my examples that I wrote out, is the same. Okay? The same. All right. Well, what about the range? Does it ever stop going down? No, clearly not. Does it ever stop going up? No. Because the y value is whatever the x value is cubed. So the y value is freaking huge, right? So again, we have negative infinity to positive infinity. And yes, as I keep writing infinities, they are getting squigglier and squigglier. Getting worse and worse. All right, cool. Well, number 4. We care about domain, we care about range. How far left, how far right. Now, this one isn't too clear by the graph because it is jumping down very quickly, right? Some might say 3 times as quickly as usual. Aha, that is literally why it's happening, is that 3 right there. And it's facing downwards because of that negative. And it starts at 5 because this thing moved up 5, flipped around, and tripled. And literally, there's the idea with transformations. I don't know why it's not taught earlier. It could be, I don't know. But yeah, so essentially we have this funky shape, but the basic version of this shape is still one of these guys. Still one of those. So does it ever stop going to the left as it follows this curve? So the same question, if I looked at the formula, is there anything I could plug into x that would break it? Is there anything I can't plug in? No, right? Whatever I throw at x, it just gets squared, multiplied and added and whatever, I don't care, but any number plus 5 is still a number, right? So the same domain happens again. That is my bad. I should have made better problems. These problems all suck. My bad, guys. But the range, well, it stops going up at one point, right? Now, on a problem like this, you might be tempted to say, okay, yeah, it goes 5 all the way down to negative infinity. No, they always have to be written down to up. Always, always, always. They have to go from the lowest value to the highest value, no exceptions. So you would start with the negative infinity and you go to the highest point, which in this case is 5. Domain is always left to right, range is always low to high. No exceptions ever. Okay. Cool. Those ones, domain and ranges suck. Let's do 2 more. Pretend that passes the vertical line test. I don't care. Yeah. Those letters in that circle are absolutely on this side of my hand somewhere. Okay. So, weird ones. Those following along at home. Don't draw this lower than that point. And put whatever squiggle you want in between. Okay. So we got domain, we got range. There's a line segment. Look at that line segment. That is the segmentiest line segment I've ever segmented, right? Ah, it's beautiful, just chef's kiss, right? All right. So, domain. These ones, these actually have answers, right? So, how far left does this guy go? 1, 2, 3. All right. I don't care about the Y. I care about the X on domain, right? So this goes to a -3, including that point. Okay, what does it go to? As far right as we go is over here, right? So 1, 2, 3. All right. Now again, I don't care about the Y values. One thing I've taught people to do. I'm muted. Uh-oh. No? It says I have a mic. Turn your thingy up. Can you guys hear me? Am I rambling to myself? Volume's all the way up. Try, try, I don't know why I'm trying to talk to you because you can't hear me. I'm gonna private message you here, okay? Okay, for the people that can actually hear me, give me a minute, because yeah, she can't hear me, I don't know what I'm saying. Your turn.
Excellent.
Yeah, but even if you play with the volume settings, if you're muted, it would unmute automatically.
Yeah, or you'll have an X on your
Yeah, you would see it.
picture, yeah.
You would
This is
see it.
mute.
Yeah, I'm not, there's a base level. If you made it to a Zoom thing, you know how to play with volume. There's a base level.
Yeah.
I mean, hell, I have a math degree. I still don't know how to use that camera. I don't know how the hell that camera works.
Never mind, I figured it out. I was connected to some AirPods. I didn't need to be connected to.
That makes sense. That makes sense. Well, cool. You gave me a minute to wipe off my glasses anyway, which is great, because honestly, I was getting all smudgy. I didn't realize I was blind. I mean, I know I'm blind, but I didn't realize I was that blind. Cool. Da, 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 da. Now everybody can hear me. I'm happy about that. Yeah. Can listen to my rambling. Okay, so domain, again, it's as far left as it goes to as far right as it goes, right? So again, we started over here. We don't care about the Y. One thing I like teaching people about this is if you're looking at domain, kind of think about the graph like smooshed. There is not a formal way of writing that, but just think of it getting squished like that, right? Like you'd still have the X, but you wouldn't have the Y's, right? So you'd just be thinking about left to right. So left, we go as far as -3. Right, we go 3 to the right, right? Cool. So we do 3 to the right, and again, it includes that point. So we use a bracket for the interval notation. Okay, now the range. Range, again, you start from the bottom value, go to the top value. It's always on the Y, right? So the range, we don't care about starting from here. We're not looking left to right. We're looking low value to high value. Again, think of it going squish that way, right? If it's squished, that's my technical term for the day, squish. This would be the lowest point, right? And that's the idea. You look at the lowest point overall on your graph, not left to right, not over in this section, overall lowest point right there, right? And which Y value is that? -2? Cool. And we're including that point, so we have a bracket. So we go -2 to what? -2 to what? The highest point. This is the highest point, even though it's on the left, I don't care, it's the highest point. 1, 2, 3, cool. Highest point's at 3, Y value is 3. 3. Yay, we're happy. Look at that. Domain and range. Let's do one more. Let's do one more. Hey, look at that thing. What the hell is that? I couldn't get an equation for that if I tried. I would have no freaking idea. It is diagonal. It looks like it started off as some kind of wave. It is changing its height. So there's a dampening going on. Like this could be an equation, but I wouldn't want to do it. And I wouldn't want to see it. But what I'm demonstrating from this example is that I really do not care about anything happening on the graph in domain and range other than the lowest point, the highest point, the furthest left, the furthest right. Everything in between, don't give half a damn. It's all about the domain and range. That's all I care about. Furthest left, 1, 2, 3, 4, 5. Okay, so that's -5. Furthest right, 1, 2, 3. Okay. -5 to 3. Okay, range. Furthest down, this guy right here. I'm gonna call that -3 because my graph sucks. There, look at that. That whole thing is that instantaneous point. Look at that,
So you gotta give us a point.
right? Man, I actually pulled it off. I thought I'd be done like an hour ago. I'm not gonna lie. We're actually doing a 2.5-hour class tonight. I haven't even gotten to the second concept. Okay, furthest down was here. That was -3. Furthest up, 1, 2, 3, 4, right there. That's the Y value is 4. I'm truly sorry for any inconvenience I caused for anyone who made plans for a short class. When I told you it was going to be a short class. I could be convinced to slap the rest of it onto another class if need be. Oh, that's right. I wanted more stuff and I didn't finish. You know what? We're rolling with democracy. Who wants to do more and who wants to call it good? I could squeeze another half hour out if you need the hours for the program. I get paid more. I'm cool with it. It's up to you guys. Otherwise, this lesson's going to be much longer. We're gonna get some- Okay, there are 5 of you. You know how many have actually given an opinion? None. Not a single one of you. I got a thumbs up. I don't know what that means. I think that means keep going. It's an interpretation. Giving you options. You know, the sad thing about democracy is, that's fair. The sad thing about democracy is that we never have all the voters come out, ever. A very small population of the country votes. Very small population of the country votes.
So true.
So, yeah. It's fun. Hi. Let's keep going. Let's keep going. Maybe I can make up some more problems. I think I could do. I got 13 problems. I probably won't go through all of those in the next half hour, right? That's probably fine. It's fine. All right. So fractional exponents. This is the first time I have gotten to teach this at any point while working for the Excel program. I have not made it this far, ever. This is cool to me. I have done functions. I have done everything we've covered so far. I have at least touched on. I have never gotten to explain fractional exponents in a couple freaking years. So this is kind of cool to me. Kind of happy about this. Kind of happy about this. All right. So the thing here, fractional exponents, well, you're familiar with exponents, x squared, cool, the exponent's 2. Well, what if that exponent's a fraction? Ugh. Right? Now, an interesting thing about these is that I have a $150 calculator that doesn't have a root button that I could plug in any root. So I actually have to mentally do the conversion to a fractional exponent anytime I have to do a fancy root in my calculator. Do you? Of course you do. There's got to be a function in this. I spent $150 on this thing.
Right.
Now, granted, that was like 15 years ago now.
Oh, yeah, that's
But-
probably why. Because
Yeah. What was that, like $20, $30?
$10.
$10. Does it $10 now?
No, it's always on sale. That's why I got it.
Okay.
Whatever it is. Texas is
30, probably.
probably, I don't know, but it was $10.
Always says at the top. 36X. Okay, yeah, all right. Yeah, no, for $10, that's a steal. I'll do. All right. Yeah, no, totally. I don't have a button for this. It makes me angry. There's got to be a function in there somewhere, but I haven't found it. Granted, I haven't gone looking hard because I know I can do this quickly. And that's why I think maybe I can get through all of these problems in the next half hour. because it's quick. It is easy. It is easy and it looks like freaking magic. It's great. So when we have positive integer exponents, so like x squared, x to the fifth, whatever, that tells us how many times that base is getting multiplied by itself. And when we have negative exponents, so x to the negative 2, if you haven't had my class before, that might throw you off a little bit, but basically you end up flipping it to the other side of the fraction when you have a negative exponent. It basically is saying how many times you're dividing by that base, right? So you end up having, if I had 2 to the negative 1, that would be 1/2 because I'm now dividing by that base, I'm dividing by that 2. So fractional exponents actually combine both those powers and the roots, the radicals, the square roots, cube roots, 500 roots. I don't even care. I don't even care. Anything. And it actually ends up being the denominator of that fraction. So the top of that fraction is always, you know, the power as usual, the exponent as usual. The bottom of it ends up being the index of the root. So the index literally just means is the thing inside the squiggly part. That's pretty much it. So if you see this thing right here, if you're like, oh my God, I'm gonna forget this, I might need to know this, I'm gonna write this on the back of my, like, I might write this on the back of my like finger or something, I don't know. That right there will get you through conceptually all of this. It should, right? Okay, so what you're seeing here is me regretting putting all of these things that close to each other because these are all separate. That probably looked really scary for a second. My bad. These are all very separate things. I'm gonna drop this guy down here. Whatever. Now they're separated and they're not scary looking, right? So fractional exponents follow the exact same rules as every other type of exponent. Only expressions with the same base or the same exponent can be simplified when you're working together. Now, what do you mean by that? What do you mean by same exponent? Because same base, I've played with those a lot, right? That actually accounts for kind of these first two right there. This one where they're multiplying and you just add the powers, and this one where they're dividing and you subtract the powers. But with the other one, I haven't really touched on that yet, okay? If you're looking at these bottom two, notice they both have the same exponent. So what it does is it kind of smooshes those bases together and puts the exponent on them. Think about that as like the distributive property backwards. That's basically what's happening. That n on the outside of that parentheses means, hey, everything in that parentheses is to the power of n. So you would normally put it on each one. Looking at it the way it's written in these images here, these examples, it's a little weirder to look at because it's kind of backwards from how I like to teach it. Honestly, I think it's easier to understand if you look at the right part versus the left part. So that's what's happening then, is they're basically like simplifying it by saying, hey, they both got the same exponent, smoosh them together, right? So it'll make a little bit more sense when we roll with this. Ooh, look at that. Look at all these beautiful examples. We have beautiful examples, right? So I'm going to write these guys out. And I'll show you a nice way of doing these where if you forget, if you're in the middle of a test and you're like, how do these work again? You can kind of pull it back, right? Because one of the things I've always been a big fan of when it comes to working more difficult problems is compare them to the most basic concept that you can for something like this. And think of this, think of it, okay, I have something to a power times something to a power. The somethings are the same, right? So think about what happens if I had something similar. If I had something similar, x squared times x squared. Well, this is two x's multiplied together. This is another two x's multiplied together. So if I'm multiplying all of them together, I would just end up adding the powers, right? And I would end up with x to the fourth. Okay, makes sense. How does that relate to this? Well, I have the same base and the powers got added, right? So if I have the same base, then you would add the powers. What's a half plus a half? 1. I'll just have that as an in-between step for funsies. It's just a 4, right? This is saying I have half of a 4 times half of a 4, kind of, sort of. Not bad, not bad. Okay. Let's see, what's my next one? My next one, convert the following to exponential form. So for the rest of these, I don't have a whole lot of math involved. They're just being able to switch back and forth, right? I'm going to write all of these next 4 down real quick. Okay. So these are actually a lot easier to work out when you're jumping right into it, right? Because we have that formula where we're going from one to the other, but it's kind of weird to look at formulas, right? So let's actually put it into play here. So we need something, we need to turn this into something with an exponent. So the first thing to think about is, well, the fractional exponent always has a power, and it has, you know, that index of the root, right? Well, what's the index of the root here? Well, if it doesn't have anything here, remember we're assuming that to be the square root, right? So we're saying this is the square root of x. The square root would imply 2, right? Okay, so that means we have x to the power of something. Now, it's going to be a fractional because anything dealing with that root is going to turn into a fraction. It's going to have a denominator. So the root part is always going to be the denominator of the fraction. The numerator of the fraction, the top part, is always whatever power we have here. Well, we don't have a power, right? How many x's do we got? 1. So what's its power? 1. Okay. Not bad, right? Not bad at all. Number 3. We have the cube root of 4. Does it change when I have a number versus an x? No. The same idea, right? We have a thing with a root, and its index is 3. Okay. Well, all that's really going to do is give us a denominator of 3. We don't have any powers on this guy. So there we go. Not bad, right? Now, I don't think you need to know this, but I can make it worse. I could simplify this. I'm gonna box these so you know that's where I was aiming. Let's make this a little bit worse. Let's make it a little worse, right? Because 4, what's 4? It's 2 squared, right? Oh my God, what's he doing? What is happening right now? What is happening? Well, the same thing we've done before. If we have an exponent on the outside of a parentheses, that means it multiplies onto every power on the inside, right? Fractional exponents, they follow the exact same rules, no exceptions. Same thing happens. So what do I end up with? Well, if I multiply 2 by 1/3, that's 2 2/3. So 4 to the 1/3 is exactly the same as 2 to the 2/3. And you can kind of see that 4 to the 1 is the same as 2 to the 2nd. The only difference here is that since this one was in a root, they just happen to have the denominator of 3. That's the difference. Not bad, right? Okay, well, what about this thing? What the hell's going on here? We have a fraction in there. What do we do? I don't even know if I've done a root of a fraction in this class. Or the last class, actually. I think I did roots in the last one. I don't remember at this point. It's all running together. So, well, we got a 5 here. We have no powers here. So we know that it's going to change to a 1/5, right? Well, what happens here? Are we content with this answer? You could probably get away with it. But you could simplify that further. Just like we could simplify that one further. Why did I jump to this one and skip that one? I don't know. My brain scoop. We're going to go back to that. Don't worry. Ha ha. This is the last one, not that one. Okay, cool. I just naturally moved to the right. I just completely skipped this one. Awesome. All right. So what happens when I have an exponent outside of a set of parentheses? It distributes to everything inside the parentheses. Every time. No exceptions. These are no different. If I had a square here, it would still distribute through there, right? Well, we end up with 1 to the 1/5 over x to the 1/5. What's 1 to the 1/5? What's 1 to anything? What's 1 multiplied by itself however many times? It's always going to be a 1, right? That's about as nice as I can make that. That's about as nice as I can make that. That's where I'm rolling with it. You know what? You guys got enough skills for that. We can roll with this one. I like that. But what do we do about Mr. 4 that I almost skipped? Oh, snap. What do I do with him? What's he doing there? Same thing as always. I have this 2x in a set of parentheses, just so you can see that, hey, it's just that thing to that power. So when I convert it over, it's still going to be that thing in the parentheses there. It has its power is 2, but we also have the root changing in. So we have the 5th happening, right? So we take the power, that's the top. We take the root, that's the bottom. So we end up with 2x to the 2/5. At this point, you could normally distribute through to each the 2 and the x. I think that'll look ugly. I don't want to do it. Let's skip that idea. I don't want to. I don't want to, right? As long as you understand, hey, these guys just kind of do that, peachy. We're good. At least for this level, right? when you start doing math where you combine and multiply these things a lot, it starts getting weirder. Not really weirder, just a little tougher to follow. Okay, well, those aren't bad. What about the other ones? 6, 7, 8, 9, and 10. I'll write these out real quick. The fun one's gonna be the last one there. Doesn't look harder, but it's gonna be. Yeah. So these ones, we are converting to the root notation, to the radical notation, right? Okay. Well, after we've gone through that stuff, going backwards is a little bit simpler, right? We have the 1/8 power, and we can immediately say, hey, if I was converting that to a root, this 1 would be the power, and the 8 would be the root, right? The index of the root. So we would have 8 root of this thing to the power here. Well, it's just to the first power, so I don't really need to put the parentheses and put a 1. I can just do a 3x. Right? Quick, simple, easy, beautiful, not bad, right? Now you might look at number 2. Not number 2, number 7. God, I have a bunch of them in a row here. Might look at the number 7 and say, okay, well, this one's going to be about just as easy, right? Wrong. There is a trick here. The trick here is, where's the power? It's on the x. Is it on the 5? Nope. So only that x is getting that happening to it. The 5 is outside of that whole thing. So with the x, it has a power of 2, and it has a root 3. So we have 5 times the cube root of x squared. Okay?
Nice.
They're not too bad, right? Okay. What number 8? You're gonna say easier, harder, or just the same? Exactly the same. Because we have a 1/2, which implies a square root. No powers here. We don't have to play with anything. In fact, we don't have the skills to play with anything there until the next week, when we start playing with binomials like that. Yeah, there's nothing we can do here. These don't combine, they don't have powers, we don't play with them at all. So we just end up with the square root of that. There's nothing we can do with that, right? It just is. Just radical. Not bad. Okay. All right. You guys think about number 9? The 4, a W, and a Y. And it's a 499 over 500 power. It's not any harder than any other problem. Every single one of these, this is the power, this is the root. No change. If it gets big, I don't care. It follows the same rules. It's going to be the 500th root of that thing, and note that I am keeping it in its parentheses because that 499 power would have to go to each and every one of those. Now, I'm not going to distribute that 499 to each of these because it wouldn't do anything for me. Now, you want to be really ridiculous, I could do that and then take that 4 and break it down like I did up here to a 2, and then I would have, what is that, the 998th power of 2? That would happen, but I don't need to do that. We're just going to call it good there. Okay. How about number 10? N to the 7/3. I said this one's going to be a little tougher. I wasn't lying, because we can, you know, switch it out right away, right? We can immediately say, oh, this is a cube root of n to the 7th. Why is that harder? What the hell, man? What are you talking about? Well, this isn't simplified. This is a cube root, and I got 7 of them. If I have 7 of them, that means a bunch of them could come out. Now, for those of you who aren't as familiar with the root stuff, basically what's happening is we have these things multiplied by themselves that many times. But anytime you have a root, if I have, say, if this is a cube root, if I have 3 of something, the cube root of that thing cubed can come out, right? Because they kind of cancel each other. You know why they cancel each other? Because they would be to the power of 3 over 3. So that group can come out. That group can come out. Anytime I have that many of a factor inside of that radical, inside of that root, you can pull it out. So this one would actually come out twice. So I would have an n and another n multiplied together. So I would have 2 n's multiplied together. And then I have the cube root of, what do I have left? 1n. So I have n squared and the cube root of n. Now you might look at this and say, I can't remember that. I won't be able to remember that. Is there another way I could get around doing some weird stuff like that? Well, if it's as nice as being a variable, yes, you can. If it's more complicated, if you got a bunch of numbers and letters inside, probably not. You're gonna have to rough it. You're gonna have to figure out. Again, I like to do factor trees. If you want to, you can always go back at one of the recordings of my previous class and see me work those guys out, because the root lesson I did on there, actually part of this unit that I'm covering right now, I didn't realize that I covered already, because I was supposed to do higher roots and fractional exponents, and the higher roots I taught all at once, because the way I like to do these, the square roots, the cube roots, the 100th roots, they are all as easy as one method. You have that many of a factor, you pull it out, period. I don't care how high your root is. If I had, that's why this was a 500, this was a 499. If this was a 501, I'd pull one out. If I have more than that power or that root, it can come out. Now, you want a cheap way to do it? If you only have one thing to that power, if I have n to the 7/3, turn that into a proper fraction, or a mixed fraction, if you prefer that term. I would look at this 3 and say, how many times does that go into that 7? Twice. with one left over. Hey, look, I have my n squared and I have my n to the 1/3. Is that cheap? That's cheap. It's cheap, but it works. Is that something you're ever going to see in a math book? No. That is actually the first time I've written that down. I made that up. It will work every single time. 100% guaranteed. It's cheap, but it works. But again, if you get something more complicated, probably break that. You could probably do a bunch of separate ones and then cram them back together at the end. That would work. Okay. Do I want to do the next three, or do I want to save those for the review next time? Let's take a look. Let's take a look. These are, ooh, those are nice. I couldn't do these in the next 4 minutes though. Well, I could do the first one, maybe the second one, not the third one. I don't remember what I was going for on that third one, actually. I'm not gonna lie. Oh wait, no, yeah, I do. All right, whatever. So I'm gonna call it good. We're gonna do these guys as part of the review next time. It's gonna be fun. We're gonna like these. I'm probably gonna break out some harder examples for fractional exponents. So be advised on that, that the preview next time is gonna, or review next time is also gonna be a bit of a lesson in itself as well. But otherwise, I am blown away by the fact that I made it 2.5 hours this time, because I thought this was gonna be, like, last time I went through more slides than this.
Yeah, exactly.
I went through more slides. I didn't think that this was gonna last this long, so that was awesome. I hate estimating time on these things. All right, guys, you are free to go. I'm going to go to sleep because I have to get on a bicycle by like 5:30 in the morning. Yeah.
All right.
Have a good night, everybody.
All right, man, you have a good one.
And
Bye.
later.